Here's the fourth video for chapter 13, and it's the last of the colligative properties. So we've already seen that vapor pressure goes down, boiling point goes up, and freezing point goes down. The last one is this thing called osmotic pressure. What osmotic pressure is the pressure required to cause osmosis to stop. So osmosis is the flow of water from an area where there's low solute to high solute, or you can say a higher solvent to lower solvent. So the movement of water, and the greater amount of solute particles that you have in a solution, the greater the osmotic pressure. Here's our equation. Pi stands for osmotic pressure. We know I because it's von Hoff factor. N over V is for molarity here because it's moles per liter, which is volume, moles per liter, times R, which is actually our gas constant, and T for our temperature in Kelvin. So the only tricky thing here is determining what's molarity versus what sometimes is molar mass, which we'll see here in a second. So this capital M is going to be molarity. So the average osmotic pressure of blood is 7.7 atmospheres, 25 degrees Celsius. What concentration of glucose will be isotonic with blood? So once again, if you're using R, be sure that you're careful with all your units, and including that is pressure, which has to be in atmospheres. So it already is in this scenario, which is fine. I plug in my osmotic pressure. Glucose is a non-electrolyte, so I is going to be 1. I'm looking for concentration, which is molarity. Here's my gas constant, and here's my temperature. So we can solve for the concentration. A lot of times we will use these 4 colligative properties to figure out who a solute is. And a lot of times we'll do that by finding out what the molar mass is. So here we've got an example. A solution of an unknown non-volatile electrolyte was prepared by dissolving 0.250 grams of substance in 40 grams of CCl4. The boiling point of the resultant solution was 0.357 degrees higher than that of a pure solvent. Calculate the molar mass of the solute. I'm realizing that this really should say non-electrolyte up here, because if you're a non-electrolyte, that would tell us that your I is equal to 1. You have to be told here what the I value is in some form or another, because you don't know who the substance is. So this really should have said non-electrolyte, and therefore I would have been 1. So here, if we're working with boiling point, what I go do is find the equation that helps me with boiling point. So delta TB equals KB times molality times I. Another thing to notice is that if you are looking for molar mass, what you are really looking for is how many grams are present and how many moles are present, because we're looking for this ratio. So what I do is I go through my given information, and I already know the grams that are present. It's 0.250 grams of the substance. He's a mystery substance, but I do know how many grams. So then what I'm going to do is go try to find the amount of moles that are in the solution. So here we've got molality that we can find using this equation. So what it tells me is that the change in boiling point was 0.357. That'll be my delta T. My KB is the 5.02. That would have had to be given. That's a constant. I'm going to look for molality, and my I is 1 once again because this should have said non-electrolyte. Now, sometimes you don't know what order you're going through. So really just plug in what you know and find something. So if molality is something I can find, let's go do that and see how it could be helpful. So here I found my molality to be 0.0711. And what we know is molality is equal to moles of solute over kilograms of solvent always. So I go back into the problem, and I see that there were 40 grams of the solvent, which means I know molality already because I just found it. I know my kilograms of solvent because I can take 40 and divide by 1,000, which means I can now calculate the moles of my solute. So I cross multiply these two values, and I figure out that in that solution there were 0.00284 moles of solute. Now I can come back over here and plug in my moles, because remember, molar mass is grams per mole. So there were 0.250 grams and 0.00284 moles. So we divide this out, and our ratio comes out to be 87.9 grams per mole. So that one used boiling point, but you could use any of the colligative properties that are given to you. So here for the next one, it's going to use osmotic pressure. As soon as I see osmotic pressure, I know that I'm going to have to go find that equation. So pi equals I mRT. I'm looking for molar mass. So again, I'm looking for grams of solute and I'm looking for moles of solute, both about the solute. So let's go through and see what we know. We know that there's a protein that's been dissolved. This protein, there's 3.5 milligrams that has been dissolved. So we can divide that by 1,000, and then we already know the grams again that were in solution. What I'm going to have to go find is the moles. So I look for pi equals I mRT. I don't see plain moles in here, but that's okay. This is what I have to work with. Remember, since R is involved, my pressure has to be in atmosphere. So I'm going to take 1.54 torr and divide by 760. That'll give me the atmospheres. I is going to be 1 because a protein is a non-electrolyte here. The molarity, I don't know that currently. I know R and I know T. I just have to get it into Kelvin. So first let's find molarity. And we get it to be 8.28 times 10 to the negative 5th. I remind myself that molarity is equal to moles per liter. So what I go look for is, I know that there was 5 milliliters of solution. So I divide by 1,000 to give me my liters here. So if I know molarity and I know liters, I can cross multiply to figure out how many moles of solute were present. So here's my moles of solute, which I can then plug in down here to get grams per mole, which will give me my molar mass. This is a huge molar mass, 8,450. Don't be worried, proteins are huge substances. So, you could double check yourself, but it's not unusual to get that.